Hello everybody, I'm Miguel Ángel Ceja Morales. I'm a student at postgrad in the Institute of Physics and Mathematics in the Universidad Michoacana of San Nicolás de Hidalgo in Morelia, Michoacán. I'm a student of postgrad in physics, and this day I'm going to talk about one of my investigation projects named Determination of the Thermal Diffusivity at the phase transition of surfactant solution in water using a transient thermal technique controlled by Arduino. On last year, Arduino has been widely developed, particularly in experimental field. In this work, we developed a control temperature, employ an Arduino, Mega Arduino board, and Peltier cell, and different devices. We are interested in the transition phases. Then, in this case, we work with cetyl trimethylammonium bromide, or CTAB, in water. And we use this by CTAB is a popular cationic surfactant, and it has different application. One of these, or the best application, is the elaboration of nanoparticle synthesis. Then we are interested in CTAB because it has a particular point of phase transition, and this particular point is around 25 degrees. It's like room temperature, and we are interested apply these experiments with the theory of the method of transient thermal. Then we are determining the thermal diffusivity as a function of phase transition in zeta. As a methodology, the samples were elaborated using anionic surfactant, in specific 200 millimolar of CTAB at 98% in water, and the CTAB solution was stirred at 400 revolutions per minute at 40 Celsius degrees for 2 hours. And the experimental sample were around 6.5 millimeters of thick. To do that, a reservoir has made imply a 3D printer using the ABS material, as we can see in the picture. The picture here, we have an image of our experimental. Here the reservoir is, in this reservoir is the sample, the water sample or the fluid sample, and there are the components of our work. Here is an Arduino board, Mega Arduino board. Well, the transient thermal technique is implemented to measure thermal diffusivity, in this case to fluids. The main aim of this technique is heat one of size of the sample constantly. First, the sample temperature is collocated in a constant temperature, we can say T0. Second, the sample is heated, in our case, on this experimental, is heated 3 degrees Celsius degrees to simulate a heat pulse, and the behavior is studied using the unidimensional heat diffusion equation. As we can see, the more simple, the simplest form is this equation 1, where alpha is the thermal diffusivity, T is the temperature field. Solving this equation using the boundary condition and initial condition according our experiment, we have the boundary condition here and the initial condition in this case. Then it is possible to solve and obtain the next solution, equation 2, and this equation, this analytic equation or this analytic solution is compared with the experimental measurement and using a function fit by Mathematica, we can obtain the diffusivity of the different samples. With this, we can see the figure 1 that shows the process of the method of the sample for the designated water. First, the figure A shows the temperature controller measured at the x equals 0, and after it shows the controller measure. Then we collocate the temperature at one constant temperature, in this case 30 degrees. After that, we turn on the controller and switch the temperature, increase it 3 Celsius degrees. Then the second image, or the image B, shows the behavior of the sample, but in the top, on the x equals L. In the same case, but we can see a less temperature between 27.f and 29.5. It's a difference of 2 degrees approximately. Then we draw two lines, two straight lines to estimate or to take the average of these temperatures at the top, at the initial temperature, at the ending temperature. And why? Because we need to obtain the gradient temperature to send or to put it in the equation 2 to be able to find an ideal fit. Showing the third image 3, we can find, or we can see a fit solution employing the equation 2 with the conditions and parameters, and we can estimate or find the thermal diffusivity. In the last slides, we can note, or we can observe all the behavior of how can did our experiment. Then, in this case, I present the results. In this picture, or in this image, is show the behavior of the water diffusivity versus temperature. We can note grow up in this graphic the experimental results goes from 20 degrees until 35 degrees approximately. Then we can note the behavior is just like a right line. In this case, in this range of temperature, it is the behavior that we expect in the literature. More than 50 degrees or more, we can note a behavior just more like a quadratic function or exponential function, but in this case it's just a line as we expect. By one side, in the figure 3 shows the measurements of CTAP samples. It just at different temperature. This picture shows the temperature diffusivity behavior grow up too. We can note that approximately 20 degrees, the value is 0.0013 meters. Well, thermal diffusivity meters quadrado seconds minus 1. Then the behavior is grow up, but in this point, approximately 25 degrees, in the next point, we can see a decrease of the thermal diffusivity, and then we obtain the similar behavior and increasing. And then we have a particular behavior here in this point, and we associate this particular point with the phase transition. Then in this case, we have the behavior as a slope with a line with different slope. Then we associate this change of slope with the value of the phase transition effect. Then, as conclusion, for the setup measurement, we observe exists an interesting behavior in the phase transition point. Then we associate different slopes in these cases, something like that, different slopes. Then with this, in this case, is from temperature. Then if by other side, if we observe a different slopes in a new measurement, we can say that there is a point in this material that we can associate with the phase transition of this material. To do that, we will implement a future works or a future experiment to make this. How we can make different experimental changing the concentration. In this work, the concentration is 200 millimolar. Then we can prove 100, 300, 500, or include or more. If we be able to observe this behavior of these slopes, we can affirm there is a phase transition to reinforce our work. But it's just difficult for the time because the experimentals are around two days approximately. We need to measure one sample one day or including more, because every point in the last graphic is just 3 experimental, and one of these experiments is 1 or 2 days, then it take time. Well, yeah, and another additional to our experiment or to work is improve our system. We are going to implement a new device to reduce the noise signal, because our signal bar error is between 0.5 Celsius degrees, and we are trying to improve this, reducing the noise, and with this we obtain a better fit in the mathematical function, or in this with the solution, comparing the solution and the experimental with the fitting in using mathematical, and we improve this with applying this device. This device is elaborated different circuits and different things. Well, that's it.